All right. So this should be familiar. A lot of people like to end on a good note with different sections, and this will be familiar stuff to you. You did this in Algebra 1, System of Equations. So first let's look at how you guys graphed two lines and how they intersected, therefore giving your solutions. And then we're going to jump to a line, and then like here, this is an inverse graph, or over here a circle. And then we'll jump to just two conics intersecting with each other, like a hyperbola and an ellipse, or a circle and an ellipse, right? And see where they intersect. So just remember that the easiest way to understand these is really the graphing approach, which is just to see where they intersect, and those are the answers. But we're going to do these algebraically because at some point you start getting radicals and decimals and things like that, which you can't get the answers for those off a graph, right? It's near impossible. So first, let's look at Algebra 1 and a little review. You'll notice you're going to have some factoring and things from Algebra 1, a lot of Algebra 1 review stuff. So, nice little review built in. So first thing is we have this elimination method. Okay. Sometimes that's also called the addition method, because you end up adding to cancel out one of the variables. So in order to solve anything with two variables, you need two equations. In order to do that, you just do this strategy to basically combine two equations into one so that it only has one variable. Because we can solve one variable equations, known as linear equations, very easily. All right. So something like this, we look for an easy multiplication. We can see, well, if this was a negative 3y here, well, that would cancel out with a positive 3y very well. So we can't just multiply the y by 3, though. We have to multiply the whole equation by 3. So that will in turn become just 9x minus 3y equals 15, right? And the top will be unchanged. Now, if we needed to, we could multiply top and bottom by different numbers if needed be. Okay. So hopefully this looks familiar, the initial setup, and then the whole idea of eliminating is right here. Eliminating means it equals 0, right? So if we add it up, it'll equal 0. So there we go. So we got 11x equal to 11. So we have x equal to 1. Now you can take that answer. That's not the answer, of course. The answer is going to be a coordinate. Like, where do these intersect, right? If we graph two lines, where are they intersecting? So we need to plug it back into either equation to find out what y is. So you can plug in the top, 2 times 1 plus 3y equals negative 4, solve that. Or plug it in the bottom. Use the original one, not the one that you multiplied by. So you wouldn't use the 9x one, but you could use 3x minus y equals 5, so I'll use the top one. So we got 2 times 1 plus 3y equals negative 4. So that'd be 3 times what equals negative 6, and y will end up being negative 2. So our solution would be 1 comma negative 2 for that. All right. So hopefully that looks familiar. Again, it's called the addition method. Now we have this other method called the substitution method. All right, right here, substitution. That's where we take one equation, plug it into the other. So for this, you had to get one of the two equations equal to y or x. It didn't matter. So looking at these, you could solve the top for x and y, but you end up with fractions because you'd have to divide by 2 or divide by 3, depending on what variable to solve for. But down here you can see we have minus y, so it's really easy just to get this to be y equals by adding y to both sides and then subtracting 5. So I would probably choose this bottom equation if I was going to do the substitution method. I'm going to show you both ways. It's going to come out to the same answer, but just a reminder that how to do all these. We'd add y to both sides, subtract 5 on both sides. Our goal is to get y by itself, and you want it to be positive, of course. So we end up with 3x minus 5 is equal to y. Okay? So this y is the same as this y. They're the same exact value. We just don't know what the value is. That's what we're trying to figure out, but they're the same number. So I can take this equation and replace this y, take it out, and then put 3x minus 5 in its place. Hence, substitute it. Okay? So we have 2x plus 3. And then I'm going to substitute in 3x minus 5 in its place. Still equals negative 4. So top equation, just took out the y, put in 3x minus 5 in its place. Now we have, again, one variable, one equation. We can solve that, no problem. Use all the normal steps that you're used to. So we got 2x and 9x and negative 15 equals negative 4. And you'll notice the same numbers come up here that come up in the addition method. So we have an 11x once again, like we did right here, 11x. And this, if you add 15 to both sides, you end up with 11 as well. So you can see in the end, it comes out to the same work. Right. So, of course, we'll get the same answer. Just because we're using a different method doesn't mean we should have a different answer. All right. We just go here and plug it into, even though we know what the answer is going to be, we can plug it back in. 2 times 1 plus 3y equals 4. Nope, equals negative 4. And this is just the same work that we already have. So, system of equation two ways. First by elimination, second by substitution. And you can use either one of these on all these problems. That's why I'm going over both. Okay? And sometimes you can eliminate, and you have to use substitution. Sometimes substitution would be almost impossible because you'd be doing a bunch of square roots and things like that. Okay? Now, keep in mind that this is just two lines intersecting someplace. So for all the problems, you can always go to Desmos, since it's a graphing problem here, and you can just take both of those, graph them, and you can see where they intersect. All right, so don't lose sight of what we're really doing here. We're just seeing where these graphs intersect. Doesn't matter if they're lines, circles, ellipses, hyperbolas, right? Circles, doesn't matter. So Desmos is your friend to check your work. Okay? So Algebra 1, nice review. Okay? So let's go down and say, let's keep one a straight line, linear, and one of them is not, right? So technically this one is not a conic section. It's going to be an inverse function, but it still works. Notice how you can have 0 solutions, 1 solution, 2 solutions, right? So think about why, because they can intersect or not intersect. That would be 0. So 0 solutions mean these things don't hit each other at all. 1 solution, of course, hits at one time. 2 solutions twice. Right? Just depends how it looks. So looking at this, you can see that there's no way to do elimination method because that requires addition, subtraction on both equations. Whereas here, there is no addition, there is no subtraction. Elimination method or addition method does not work. So we have to take the bottom equation and do substitution. So sometimes that's the most difficult part, is just figuring out what can I do, or what can I do. All right. So let's solve this for x or y. What do you think? We can subtract y on both sides, and then we have x equals, right? Simple. You could have subtracted x and done the same way. Wouldn't be wrong. So we'll use these two equations. Right. Now, before we get too far, sometimes it pays not to overthink it. What does what does all this mean? Think about what this means. Two numbers multiply to 8. The same two numbers add to 6. What are they? 4 and 2. Right? So you can always don't overlook the, sometimes the obvious, right? So keep that in mind. 4 and 2. Okay, so let's go through that and kind of anticipating that's where we're going to end up. So do some substitution. So I'm going to take 6 minus y, substitute that in for x. So I have 6 minus y and equals 8. Let's do some distributive property. So I have 6y minus y squared. It's now a quadratic equation. So the solving is different. It's not going to be just variables on the left, numbers on the right. It's quadratic, which means factoring, quadratic formula, all that good stuff. Box method, all those things. Recall that when you're doing quadratic solving, it has to be equal to 0, and you want the y or the x squared, whatever's quadratic, to be positive. So while you might be thinking, well, get it equal to 0, subtract 8, you probably want to move the left side to the right side just so that the y squared is positive. The factoring just is easier when you have a positive quadratic term. And that means we also have to move the 6y. So goal number 1 is accomplished. I have it equal to 0 by doing this. Write this in descending order, so quadratic term first, linear term second, constant term last. All right, how does this factor? Okay. So you guys know a variety of methods, like what two numbers multiply to 8 and add to -6. That would be one way of doing this. Any takers on that? Multiplies to 8, adds to -6. -2, -4. There we go. And it's really important that these equal to 0. The question comes up, well, why does it have to be equal to 0? How come not 1 or 2, whatever? It's because at this point, we can use a property called the 0 property of multiplication, because anything, well, to get an answer of 0, either this number, y minus 4, has to equal 0, or the other number has to equal 0, because the only way to get 0 is to multiply by 0. Okay? That doesn't work with any other number. So it's super important that this number equals 0. So we got two answers here. No surprise. Got 4 and 2. Right? So we have to take each one of these numbers here and plug it back in. Right? To either one. So first we can do like y equals 4. Say if we substitute y equals 4 back in, we'll have x times 4 equals 8. So of course x equals 2. Therefore getting 2 comma 4. And we expected that, but notice how we still have to do the other one. And it might seem redundant, but it's actually probably the most important part of the problem. Everybody guessed 2 and 4, but did you say to yourself, oh, 2 and 4 and 4 and 2. There's two answers. See, that's the thing that might be lost just by looking at it on the surface. So, yeah, we technically have two different answers, two different intersections, two different coordinates. 2 and 4 and 4 and 2. Those give us our answers. Now, if all this seems relatively simple and review-ish to you, focus on how you write your work out, just making it clear, clean, writing the work all the way down. There's a tendency for, I don't know, every now and then there's always one or two in the class that says, well, at this point I kind of knew what the answer is and I just stopped writing. Okay, so just know you'll get the points for the work that you show, not for the stuff that you think. So if you want credit for full credit, show full work. It's not for you. It's for the reader to understand what you're thinking. It's kind of like if the author of a book starts writing it, the ending of it, and thinks, you know what, I know what the ending is, I'm just going to not write the rest of it and let everybody else figure it out. It doesn't make sense. Even though the author knows the ending, they still write it down for everybody else to know. So all the little details, please write out. Do not skip it simply because you feel like you can get the answers without any further writing. I know it's a little cumbersome, but we want to be thorough and careful. So once again, let's look at what this looks like. You know, if you always want to get a graphical one, so let's go to, let's see here, A. Yeah, so it looks like this. So we have that inverse function, and then we zoom in, so it just looks like this. We got 4, 2, and 2, 4. Just cutting that just barely. Again, another reason why we don't want to depend on graphing only. If we had to graph this by hand, and we didn't have these nice, you know, lattice marks here, it'd be very hard to tell that these are the answers. So algebra, which is the substitution method here, is necessary to know how to do all this stuff. Alright, so hopefully that's working for you. Not too bad, right? Getting the swing of things again. Let's see here. Alright, let's keep going. Now, if you want to try to do this in front of me and just follow along, you can do that. If you think you get the hang of it. If not, just, you know, stay with me. But you might feel confident at this point to try it out. Once again, the beginning is probably the first and most creative part, is just figuring out what you can and can't do. Here again, we have something we can't do addition method because of these are linear terms, right, or to the first power. These are quadratic terms to the second power, and those don't add up. So there's nothing to eliminate here. So we have to do substitution once again. The easy method would be just to add y. So we have x equals y plus 1. Substitute that back in for x right here. Okay, so we got y plus 1. Quantity squared plus another y squared that was already there. That equals 25. Okay. Little sidebar. What is y squared plus 1 squared? Sorry, y plus 1 squared. What does that equal to? So, little reminder that y plus 1 quantity squared does not equal y squared plus 1 squared. So for those getting creative and saying, you know what, I just remembered in this last problem, over here, where was it? Was it up here? Yeah, we did some distributive, so I could just multiply this times this and get 9 times 15. Shoot. Why not just start doing that with exponents and start doing that? It just does not work. Okay, so don't do that. If you need a little justification, just go ahead and do your boxes here, like that. Alright, just a little reminder on why that doesn't work. So yeah, you get the y squared. Yeah, you get the 1 squared, but you also get these two other values. Alright, you get a 1y here, a 1y here, thus giving you y squared plus 2y plus 1. So that's why we don't distribute exponents. You have to multiply them out. See, nice good review. Okay. Now we have a quadratic still, meaning we still have squares. So I'm going to have to do what we did in the last problem, get it equal to 0, factor, and all that good stuff. Same thing. If these came out to just regular y's, it'd be linear. Variables on one side, numbers on the other, and divide. So let's do some grouping. Let's see here. We got a y squared and a y squared. That makes 2y squared. We got a 2y. Let's bring that on down. And now we got a 1 and a 25. Remember, we want to get equal to 0, so we're going to subtract 25. So we actually get negative 24. And at this point, you could do the factoring, but if you're careful, you'll notice this has a GCF of 2. That's a good thing. That means we can factor that out. And it makes all the numbers smaller. You can still factor it here and get the same answer, but the factoring is a lot easier if you take out a common factor if it is there. It doesn't have to be there, but if it's there, it's awful nice. Yeah, so that doesn't always happen where you get that number that goes in evenly into all three terms. But here it does. So now we can do the factoring. Back to our usual steps. What multiplies to negative 12 adds to 1. That's a 1y. So what are the two numbers that work there? Any takers? 4, negative 3. 4 minus 3 equals 1. 4 times negative 3 is negative 12. Now, since this 2 doesn't have any variable, we kind of ignore it at this point. Okay, we could say 2y plus 4 equals 0, but in the end it doesn't change the answer, so we just kind of ignore a numerical GCF here and say, let's focus on the variables only. So we got negative 4 and positive 3. Okay. Just like before, we have to plug each one of those back in to see what the answer would be. So we got y equals negative 4. And technically you could use either. Obviously the top one is a little bit easier arithmetically, so I'm going to stick with that. Get x minus a negative 4, so notice that this minus sign is not the same as the negative sign. There is a minus sign, there's also a negative sign, so we got both. Common mistake. So what plus 4 equals 1? What number plus 4 equals 1? And that would be negative 3. Negative 3 plus 4 is 1. So we got our first solution, negative 3 comma 4. Right? And then do it one more time with our other solution down here, y equals 3. And you'll see how often you get answers that are like opposite of each other. So we had a, we have a negative 3 and we got a positive 3. You got a lot of the same numbers floating around, but maybe with a different sign. That's not uncommon at all. So more of a good reason to make sure your signs are correct. So what minus 3 equals 1? You get 4. So that's our other solution, 4 comma 3. And you could probably, look at this and, know how to mentally graph this, so it doesn't hurt to think about it. All right, this is a circle, right? Both positive. Centered at 0, 0. And since it's 25, we know the radius is 5. So this is a circle with a radius of 5. Something like that. And our answer says, okay, the straight line here, this equation, is going to intersect at -3, 4. -3, 4, that's up here. And 4, 3, that's up here. Does that look right? Anything off here? Aha, -4, right? Yeah. So, yeah, that was in y equals -4, so I mislabeled it. -3, -4, down here. There we go. That looks like better graph. So little details, right? Little things. So goes the story in math. Once you know how to do all the new stuff, you generally make mistakes on the old stuff, the little things. The more careful you are, the better. Okay. And a more precise look at this one. Yeah, looks like that. There we go. So Desmos is your friend if you want to check or if you're just stuck. Okay, that's pretty good. Okay. Lastly, we got one more set, one more example, then I'll let you guys do the last one. Pushing it today, huh? Let's see. This is your silent lesson in situational awareness. Don't go about making noise in a quiet room. Alright, so conics have a little bit more going on. As you can see, we have 0 solutions, 1 solution, 2 solutions, 3 solutions, 4 solutions possible. Alright? So the more complex the graphs, the more ways they can intersect. So the way you'll know you get 0 solutions, by the way, is that you'll start seeing square roots of negatives. So there's no imaginary answers here. So if you see square root of negatives, don't start saying, oh, the answer is, 5i or something. Just say, okay, when you're graphing on, regular xy coordinates, no solution, because we're not graphing in imaginary coordinates right now. Okay. So one solution is usually like a vertex hitting the tip of a circle. Just touches it once, comes back off. So you can have like, something like this. All right, that would be a good one solution. Another circle, 2 solutions could look like this. All right, 3 solutions, you could have like a hyperbola and an ellipse where it crosses 1, 2, 3 times, something like that. All right. Lots of different possibilities. These are just a few. Just know that it is possible to have these all different types of solutions here. 4 solutions would be a good one. Circle and an ellipse going all the way through it. Something like this. So you have 1, 2, 3, 4 solutions like that. Another zero solution could be, here's a circle, here's a parabola. They just don't intersect with each other. So no intersection means no solution. Doesn't mean there's no graphs, just means there's no intersections of the graph. So always think about solutions as an analogous word would be intersections. Sections. Yeah, there we go. All right, here we go. Wrapping it on up. And we can go back to, what's it called? Elimination method. Because we have addition, subtraction, they're both squared, so elimination / addition method, a little bit easier, a little bit faster, so we tend to jump on it when we can. We could eliminate the y's by multiplying by 2 on the top, because we have -2, +2. You could multiply the bottom by -5 and have 5x squared and -5x squared. Either one gives you the same answer. I'm going to go with the top and say we got to multiply this by, let's see here, +2, right? So we got 10x squared minus 2y squared equals 6. And bottom stays the same. Oh, nice. All right. Of course, add it up. We got 10x squared plus 1x squared is 11x squared. We got a 0 or an elimination of a variable. And we have 11 again. So that means x squared is just equal to 1. And we get x equals 1. Okay. Look pretty good. So even these problems that could have more solutions doesn't mean the problem is necessarily more difficult. Doesn't mean it's harder. It just got to do a little bit more at the on the end here. All right. So now that we did all that, what's wrong with it? Yeah, you guys caught that. Good. We took the square root of both sides. This says what number times itself equals 1? 1 times 1 is 1. -1 times -1 is also 1. So we got to have both. And this is what's new, and that's what leads us to having more than the 2 solutions that we got above. Is that when we get answers here that are plus or minus, that can lead to having the 4 solutions. Right? So now we have to take each one of these. Before it was just plug in, just the one number. Now we got to plug in both. Okay, so here we go. Let's first do x equals +1. Yeah. And let's plug it into probably the bottom one here. It's a little bit easier because it's just x squared. So we got 1 squared plus 2y squared equals 5. So we got 2y squared equals 4 by subtracting 1 on both sides. So we have y squared equals 2, dividing by 2 on both sides. So we have y equals √2. Plus or minus. So from this single x that we got here, one of 2 of the x's gave me 2 more solutions. So that leads us to having 2 solutions with x equals 1. Alright, so that one single x here is giving us both a positive √2 and a negative √2. And we're only halfway done. Right? Because we still haven't done x equals -1. So we'll do the same thing, right? And get 2 more solutions that are very similar. So if I go over here and say x equals -1, now the nice thing here is that if I use the same equation, the bottom one, I'm just going to square it, right? But as soon as I do that, it's the same equation because 1 squared turned out to be 1 and -1 squared turned out to be 1 as well. So the work looks identical. So we'll have the same thing going on here, dividing by 2, taking the square root, getting plus or minus root 2 once again, but the x's are now -1. Over here they're positive ones, over here they're negative ones. So when you see this going on, it just means graphically in your answer, it's going to be very symmetrical. Okay. So roughly, this is a circle, hyperbola on top. It's opening left and right because the x's are positive. So I know it's a left and right opening. So if I was going to sketch this, I would just estimate it looking like this. Right? With no foci or major axis, but I just know it's opening left and right. Okay? And this is an ellipse, and since the 2 is on the y-squared, I know it's going to be a little bit shorter on the vertical. So it's going to look like an ellipse like this. So you can see you get 4 intersections that are very symmetrical. 1 common root 2, 1 common negative root 2. So that would be here and here. Right? Positive 1. And then over here, same thing. -1 positive root 2, -1 negative root 2. Okay. So I'm going to ask you on your reviews and your homework, of course, you're going to be sketching these solutions. So once you get all the answers, just to roughly sketch it. You notice how this is not even close to being elliptical. You know, there's no numbers on here at all, just to sketch, nothing fancy. Just so you can, get an idea of what we're looking at. And if you really want to be very precise, you can jump over decimals. All right, and then you can see it that way. Right. Notice here, though, it gives the decimal. It doesn't give radicals here. So you have to know that 1414 is root 2. 1.414, 1414 is how I think about it. That's root 2. So between, of course, the option of having the decimals as your answers or the radicals, you definitely want to have the radicals in your answers, not something that's approximated. So always, 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 when possible, use the exact answer. All right, your guys' turn finally, and we'll be done. That was a little bit long. All right, give that a go, and then sketch the solutions and see what you think it looks like, and then I'll go over the answer real fast. Now you had a choice on whether to eliminate the y's or the x's. Notice how eliminating x's is way faster. So take a close look at both of them before you just start doing what comes to mind first. And the thing that's different here is that, we get 0, we're taking a square root, but there's no such thing as plus or minus 0. So you know right away we don't have 4 solutions, because the only way to do that is if we had 2 different answers here that we could plug in and then get 2 answers from each of those. So all of a sudden you can tell it's already kind of different. So when you get zeros, or if we got like a negative here, that's when you say, okay, there's no solution. All right. All right, so we go, let's see here. Plug it back in, either one, doesn't matter which. All right, y equals 0. So we got x squared plus 9y 0 squared equals 36, which is the same as just what squared equals 36, right? Because anything with 0 squared and it's all 0. So square root both sides, x equals plus or minus 6. So we got 6, 0 and negative 6, 0. So how can you have 2 solutions when you have a circle the bottom one, and an ellipse. And you notice that, again, this is symmetrical. So because there's a couple ways of having those two solutions. You could say, well, I got a circle here, and there's the ellipse. Okay, two solutions, boom. But that's not centered at 0, 0. Both of these are at 0, 0, because you know that because none of them are like x minus 3 squared or y plus 2 squared. So they both have to have the same center, so this isn't possible, right? So what it turns out to be is that we got a circle, and then the ellipse is just right inside, looking like that. So there's your negative 6, 0, and your positive 6, 0. So you see how you can arrive at this conclusion even without any formal graphing, without decimals. This is the only place you can logically land that would make sense to get two solutions. So that might be the more creative part of this whole assignment, is thinking, visually in your mind, mentally, of, well, how can I move these two shapes around so that it only contacts at two places? And ultimately, if that doesn't work, you can't remember, go to Desmos, check it out, type in both equations, and there you have it. Okay? Alright, I know that was a little bit, but we are at the end. Let me put up the homework and let you guys relax for a little bit.